Okay, I want to do one more example on combining functions, either using addition, subtraction, multiplication, or division. And I want to do an application example here. So it says that functions that model the number of births and deaths in the US for select years from 2000 through 2016 are b of x equals, and then you have that function, negative 2.6x squared plus 33x plus 43, and d of x equals 2x squared minus 13x plus 2428. And this actually was introduced in the section opener, which I don't have here in the video, but if you want to, you can go back and read through that. Now, B stands for births. Okay, and D stands for deaths. So the first function represents the number of births in a year, and the second function represents the number of deaths in a year. So for A, we want to write a function that models the change in the US population for each year. So if you think about this, the change in the population, well, births are adding to the population and deaths are decreasing the population. So the change in the overall number of people on Earth, we'll say, I guess in the US, would be births minus deaths, okay? So that's why we want this function here. So that's gonna be our first step. Okay, so we're just gonna subtract those two functions. So my B function, negative 2.6x squared plus 33x plus 4,043 minus my D function, 2x squared minus 13x plus 2428. Now just be a little careful because of that subtraction, you do need to distribute that through. So we end up with negative 2.6x squared plus 33x plus 43 minus 2x squared plus 13x minus 2428. And then we're going to combine like terms. So I have negative 2.6x squared and negative 2x squared. So that's negative 4.6x squared. I have 33x and 13x. So that's going to be what, 46x. I'll just check my work. Yep. And then the last one, 4,043 minus 2,428. That is going to be 1615. And obviously I'm just using a calculator here. So this is that final function that we're looking for part A. Use the function in part A to find the change in the US population in 2014. So for this one, you do need a little bit about the opener, but it does tell you that X is equal to the number of years since 2000, because we're starting in year 2000 here. There it is. So if we're looking at 2014, then our X value here is going to be 14, right? Because 2014 minus 2000 is equal to 14 years have gone by. So we're going to plug 14 into our function. Now, like I said in a previous video, you can either plug it into the final function, or you could actually plug it into each function individually and then subtract those values here. It's usually easier just to plug it into the final function if you have it. So I'm going to go ahead and do that. Okay, so I go ahead and I plug that in, and then I'm going to go ahead and just simplify using order of operations. So 14 squared is going to give me 196. And then for the first group, I end up with negative 901.6. For the second multiplication, I have 644, and then the 1615. And then finally adding and subtracting these all together, I end up with 1,357.4. So this is our final value there. And again, I encourage you at home to pause the video and actually try the other way as well. So if you plug in 14 to just the B function, and then plug in 14 to just the D function, and here we're subtracting, so subtract those two numbers, and you should get the same 1357.4. So it's kind of nice because you could do it either way. And it just depends on the information you have. If you have the final function, that's usually easier. But sometimes you don't always have the final function. Maybe you have a graph instead, or maybe you have tables of points or something different. And in which case you can use the individual values to help you find the answer there. Okay, so our last piece here is, does the result obtained in part B overestimate or underestimate the actual population change in 2014 based on the graph on page 300? So let me show you that. I didn't want to copy it in again. So I'm just going to bring it up on the screen. All right, so here's your text, and here's that chapter opener piece that they're looking at here. So in 2014, they had 3988 for the births and 2,628 for the deaths. So if we subtract those two numbers, then we'd be able to find out the change there. So I'm going to use my calculator here. Okay, so let's see, I'm going to type in 3,988 minus 2,628. And I see a change of 1360. So there are more births than deaths. So the population of the US grew by 1360 there. And let's go back and check our work to see if this is an over or underestimation. All right, it's a heavy textbook. All right, so the actual number we just said was 1360. And the number we got was 1357.4. This is actually really good. So it does technically underestimate it a little bit. Right, so our equation underestimates the actual value. It's a little bit lower. It does ask for how much. So if I subtract these two, so I'm going to just use my calculator, 1360 minus 1357.4. Oops. Let's see, I get 5.6. Now, going back to the chapter opener, you do actually have to know that this is in thousands. Okay, hang on, I think I have an error here. Let me fix this. 1360 minus 1357.4. Yeah, that looked too big. So this is 2.6. And sorry about that. I knew I wrote something wrong there. So that's 2.6. But if you go to the chapter opener, this is in thousands. So it's not just 1360, but actually 1360,000. So how do you fix that? All you need to do is multiply your answer by 1,000. And you could actually get that as well. So you could either write 2.6 thousand, or we could write this as 2 and then multiply it out and get 2,600 here. Okay, so we're off by about 2,600 people. Again, that's still a sizable number, but these values are pretty close here. We're only off by 2.6. It is in thousands, but it's still a pretty good estimation there. So that ends the algebra of functions. The next thing we're going to look at are called is when we compose functions. And composing functions is another way to work with them and to combine them. And it's when we plug one function into another function. So you guys have evaluated already, right? We've done things like, oh, here's my function f of x. Can you please find f of 5, right? So we replace the x with 5. But now instead of replacing it with a number, we're going to replace it with an entire function. So we're going to plug one function into another, and that's called composition. There's some new notation here. So the composition of function f with g is denoted by this. So it's like a raised open circle. And you can write it that way, or you can also write it using that notation here. Now, one thing I want to note, there's always an outside function and an inside function. So the outside function is either written first or on the outside. And then the inside function is written second or on the inside. I tend to like the second notation better because you can kind of see what's being plugged in. but they both mean the same thing. I do want to note that we read this as f of g of x. So when you have this notation, you can say the composition of functions f and g, but we often just say f of g of x. So you'll hear that as well. I do want to note that order is important. So you're going to see in our next example, we're going to compose different ways, and you often get different answers. Not always, but a lot of the time. So you cannot assume that one composition equals the other if you reverse the function order. So you need to do each of them out individually. So let's see some of these examples. So I'm going to use a linear function and a quadratic here, but again, you could see all types of functions, including your roots and your cubes and your absolute values and so on. And we're going to find the compositions. So here we're doing f of g of x. So f is the outside function and g is the inside function. The outside function is what you're going to start with, and the inside function is what you plug in. So what I usually like to do is I like to rewrite the outside function first, which is 3x minus 4. And then I'm going to go ahead and replace my x, in this case, with the g function. So my problem is going to be 3, and then my g function is this one. So it's going to be x squared minus 2x plus 6. And then I also have that minus 4. So don't forget the rest of your expression there. So we're replacing not the x with just a number, but with an entire expression, entire function. And then you're going to simplify. So I can go ahead and multiply this out. 3x squared minus 6x plus 18, and then minus 4. So f of g of x is equal to 3x squared minus 6x, and then I can combine this into plus 14. Oops. There we go. All right, let's do another one. No. Here, notice that we're changing the order. So our outside function, that's where you're going to start, is your g function. And then the f function is the inside. That's what gets plugged in. So my outside function is x squared minus 2x plus 6. And then anytime I see an x, I'm going to replace it with whatever is the inside function, which is f here. So let's see, f of x is 3x minus 4, and that is squared, minus 2 times 3x minus 4, and then plus the 6. So I guess I should have written this in a different color, but it's this piece right here. And now we're going to simplify. So here I do have to square this. So you are going to multiply that out. Okay. So I have, let's see, 9x squared minus 12x minus 12x plus 16. I multiply out the next group too, minus 6x plus 8 plus 6. And then I'm going to go ahead and combine my like terms. Let's see, I have 9x squared minus 12x, and minus 6x. So that's going to give me negative 30x. And then 16 plus 8 plus 6 is going to also give me 30. All right, and that is my final answer there. Notice that those two functions are totally different, right? These are not the same thing. So you have to be really, really careful about the order that you're using. Make sure you have the correct outside and the correct inside function. Okay. Now here we're going to evaluate, and notice that I'm using this function here. So you can do it in two ways. The first way is to just take your final function, that g of f function. We already found it, right? It's right here. So I'm just going to go ahead and plug in the 1 in this case. So it's going to be 9 times 1 squared minus 30 times 1 plus 3. Oh, plus 30, excuse me. So 9 times 1 minus 30 times 1 plus 30. 9 minus 30 plus 30 is equal to 9. So that is my result there. And again, if you have that equation, it's usually the easiest thing to do. If you don't have your equation, you can do it in 2 steps, just kind of like I showed you with the algebra of functions before. You can do the functions individually. But you have to be a little bit careful here when you do that. You always start with the inside function if you're going to evaluate. So I'm going to start with f of 1 first. So f is 3x minus 4. So I'm going to do 3 times 1 minus 4. So 3 minus 4 is negative 1. So what happens here is now g of f of negative 1 becomes just g of positive 1. G of f of 1 is equal to g of negative 1. Because what happens is this piece right here is just negative 1, right? We solved it, it's right here. So you don't need this anymore. And now you plug negative 1 into g. So now you plug it into the g function. Your g function is this one. So it's negative 1 squared minus 2 times negative 1 plus 6. Running out of room here. Negative 1 squared is 1. Negative 2 times negative 1 is positive 2. So I have 1 plus 2 is 3 plus 6 is also 9. So again, just another way that you can do it. This way I think tends to be easiest if you have that function already. But if you don't have that starting function, you can do it in 2 steps. You work inside to outside. So plug your value into the inner function first, and then take that new answer and plug it into the outside function. And you can find the same number that way as well. And again, this is helpful because sometimes they may not give you the full functions. They may give you like the graphs instead or just tables instead. And you can use this technique to find the answer still. All right, we do need to talk about domain. So domain of composite functions does have a similar idea to when you had the adding, subtracting, multiplying, and dividing functions where you sort of have to combine things together. So there are different ways to think of it. This is the way that I think is the easiest. So you first find the domain of the inside function. Then you find the domain of the composite function, so like the whole function that you found the answer to. And then you put both domains together by finding the intersection of the 2 domains. And again, for me, I think that's the easiest way to do it. So let's do one more example, and let's also find the domain here. All right. So I have my 2 functions. I'm noticing that f is my outside function. This is where we're going to start. And g is my inside function. And this is what's getting plugged in. So let's see, my outside function, I'm going to rewrite it. 2 over x minus 1. And then I'm going to take this and I'm replacing it with g of x this time. So I have 2 over, and my g of x function is 3 over x. Minus 1. Now I have to simplify. This one's kind of hard to simplify if you haven't seen this before when you have rationals like this. So what you're going to do first is you need to combine the denominators into 1. So we need to do some common denominator work there. So I'm going to do that off to the side. Let's do that off to the side first. So 3 over x minus 1. It's the same thing as 3 over x minus 1 over 1, right? 1 over 1 and 1 are the same thing. So my denominator would be great if I could make this denominator an x, then I could combine it with this one. So I'm going to multiply by x over x here. Always multiply the same on the top and the bottom. And then I have 3 over x minus x over x. And now I can go ahead and put this together. X is in the denominator, and I have 3 minus x here. So I can rewrite this as 2 over 3 minus x over x. Now I have still a little bit more simplifying to do here. So we're going to be careful. There's different ways to think of it. But one way that I like to think of it is this bar here is just division, right? So this is really 2 divided by 3 minus x over x. And if you think about fractions, we always change division to multiplication, and then we always flip that second fraction and take the reciprocal. Now this is 2 over 1. So if I multiply straight across, I'm left with 2x over 3 minus x. And finally, we're done. So our final answer is that f of g of x is equal to 2x over 3 minus x. We don't want to leave it this way. We just don't really like fractions and fractions. It gets too messy. So you do want to try to clean that up a little bit. And if you need to, you can use common denominators. After that, what we're basically doing is just flipping the denominator and multiplying it with the numerator. It will cancel out in the denominator when you do that flipping action. And then you're just multiplying it with the numerator to get the final result. So that is our composition here. And again, this is a more challenging one. Now for the domain, okay, we're going to follow our steps. So the first thing I want to do is I want to find the domain of the inside function. For this particular problem, my inside function is g of x. So g of x equals 3 over x. Now I need to make sure my denominator is not equal to 0. My denominator is x here, so I need to make sure that x is not 0. So we need to exclude 0 from the domain. The second thing I need to do is find the domain of the entire composite function. So now you look at your total answer here. And again, I need to make sure my denominator is not equal to 0. So when I solve 3 minus x equals 0, I could add x to both sides. And I see 3 is equal to x. So I need to make sure that x is not equal to 3 here, right? So again, that's a bad value. We don't want it to be 3. And then your third step is to put this together. So from the first part, x cannot be 0. And from the second part, x cannot be 3. So our overall domain are all x values, such that x is not 0 or 3. Oops. Or interval notation, we have negative infinity to 0, 0 to 3, 3 to infinity. And I'm just using those union symbols in between to represent that all 3 together are part of the answer here. And that's a harder one. These rationals can be really tricky. So not every problem is as difficult, but you do want to get in mind that you always check both parts of the composite function. Check the inside and the final composite function for the domain issues. A lot of times students forget to check the inside. They'll do the final answer, but they won't check the inside function. And you could be missing something there. So you want to make sure you check that as well and then put both combinations together. All right. The last thing here I want to talk about is decomposing functions. So we can also decompose functions, which means breaking them back down into 2 functions. So in all of the other ones, we've been putting them together, and now you can also break them apart. So for instance, here's an example. H of x equals the cubed root of x squared plus 1. So we want to know, is there a way to write h of x as f of g of x? And it's kind of like a puzzle. So you want to think, well, what would be the outside function and what would be the inside function here, right? So that's still your outside function and that's still your inside function. And hopefully there's something that jumps out at you. Usually the inside function is inside something. So here, one of the easiest things to do for this example is I could let my inside function be the x squared plus 1, right? Because it's in the root. So I'm going to let g of x be x squared plus 1. And then I'm going to let my f of x function be the outer function. Now your outer function is just right here. It's the cubed root. So it's the cubed root of x. And you can check it. So if you need to, check it, right? F of g of x. Well, this is my outside function. So I'm starting with the cubed root of x. And this is what I'm plugging in. So this is going to become the g of x function. And my g of x function is x squared plus 1, right? And it does match. So this decomposition works. Sometimes there is more than one answer, but you want to go with the most obvious answer. So usually here, again, if something is inside something else, then that is probably your inside function. I will make a note though, that another answer could be g of x equals x squared and f of x equals the cubed root of x plus 1. So in this case, you're plugging x squared in for x to get that final result. This is not an obvious one, so I would go with the obvious answer first when you're answering questions and homework and things like that. Whatever is inside something, make that your inside function. But there could be more than one answer. So it's just something to watch out for as you're decomposing functions.